Welcome back to another Chemistry IGCSE 0620 video, and today we'll be looking at Unit 2, which is Atoms, Elements and Compounds. Again, I'm going to be following the order in the syllabus, which may be different from the order that's in your textbook, depending on what your textbook is. So, item 2.1 has to do with elements, compounds and mixtures, where really you just need to know the differences between each of these things. So an element, right? An element is just one, it only contains one kind of atom. So sodium is an element, lithium is an element, but something like carbon dioxide, which has two types of atoms, is not an element. I guess in contrast to this, you have compounds. Now, compounds are made up of different kinds of elements that are bonded together. So, let me just write that down. Compounds. They're made of different kinds of elements, they're made of atoms of different elements that are bonded together. So, CO2, our previous example, is a compound because you have a carbon atom that is bonded to two oxygen atoms, and carbon and oxygen are two different kinds of atoms for different elements. Similarly, something like lithium oxide, I think that's how you do it. Lithium oxide is also a compound. Now here's the, tricky thing. A mixture is, you need to know this, a mixture and a compound are not the same, right? Let's just write that down. A mixture, it contains different elements or compounds that are not bonded together. So compounds, the atoms, the different kinds of atoms in the compound are bonded together, whereas over here, it contains different elements and compounds that are not bonded together. That's a very important distinction. Let's just write that down. Not bonded. So examples of, mixtures would be a mixture of iron filings, and sand. I'm not sure if I spelled iron filings correctly, but you get the point. Over here, the iron is its own thing, and the sand, which is usually mainly just silica, is its own thing. They're not bonded together, they're different. Another important characteristic of mixtures is that you can separate them easily. So they're easy to separate via physical means. Easy to separate via physical means. So in the case for iron filings and sand, I can separate the iron filings from the sand by simply using a magnet. Whereas in the case for CO2, I can't separate the carbon from oxygen easily. Yeah, so that's another difference between compounds and mixtures. Right, so now the second thing that we need to look at is the structure of an atom. So let me just draw a quick figure, right? Maybe let's get a dotted brush, just a second. Right, so I have the structure drawn here. Now all atoms are composed of a nucleus, a central nucleus, right? And the nucleus is surrounded by orbiting electrons. So let's just draw that here. Right, these are electrons. Let me label one. Now the nucleus, the nucleus itself is composed of protons and neutrons. Again, this is like basic stuff that we are all aware of. And collectively, protons, neutrons and electrons are called subatomic particles because they are smaller than an atom. One thing that you need to note is that an atom cannot be broken down chemically. It breaks down during, I guess, nuclear reactions, but it doesn't, like, you can't physically break down an atom normally. Another thing is that all three of these things have mass. They all have a mass, but only protons and electrons have a charge. Let me just summarize what that means real quick. Right, so as you can see from this table, protons have a mass of 1 and a charge of plus, while neutrons have a mass of 1 as well, but they don't have any charge, which is why they're neutral, and thus that's how you get their name. Electrons do have a mass, but it's so small and insignificant that you can consider it as 0. But they have a charge of minus. So it's of the same magnitude as a proton, just in the opposite direction, if that makes sense. I say direction in quotations. Now, the important thing here is that what this tells us is that the nucleus of an atom is really what the mass of the atom has. Basically, the protons and neutrons, which are the only subatomic particles with a significant mass, form the nucleus, and that's the heavy part of the atom. While the electrons orbit the nucleus, and the only thing that they contribute is a negative charge. And because another thing is that the number of protons in an atom, let's just write that down, number of protons is equals to the number of electrons. So if there's one proton, there'll be one electron, and protons have a plus 1 charge, I guess, and electrons have a minus 1 charge. So the net charge of an atom is always neutral. So atoms don't really have a charge because of this relationship that I just showed. But electrons, they contribute a charge, but they don't contribute mass. So the mass of an atom is derived from protons and neutrons. Another thing, NB, this is important. You don't measure the mass of subatomic particles in grams or kilograms. Rather, you're using atomic mass units, AMU, which I've written here. I mean, it's not really units per se. Rather, it's just that subatomic particles are so small. At that point, there's no directive in really putting a unit. Yes, I mean, that's it. Right. So, a sodium atom, for example, has 11 protons, and it has 11 protons like this. Well, let's just, yes, I made a mistake. Yes, it has 11 protons, and then it has a mass of 23. You need to know the proton number, also known as the the proton number, or the atomic number of elements, which is just the number of protons that the atom has. That's something you have to know. You don't have to know the mass. The only thing that you need to know relating to the actual mass of the atom is that if I do 23 minus 11, I get the number of protons in sodium. And this relationship is something that you need to be aware of. Other than that, you only need to know the proton number of the first 30 or so elements. So the first 20, for sure, you need to know those. And then also some of the transition elements that come later on. But yeah, that's about it. Right. Now, I also mentioned that the number of protons is equals to the number of electrons. So in the case of sodium, since it has 11 protons, that means it also has 11 electrons. That's also a relationship that you need to remember. I talked about mass, and yes, again, you need to know the or the proton number for the first 20 elements for sure, and by proxy, you're going to know the number of electrons. Okay, quick fact, this isn't something that you don't need to know this for the IGCSE syllabus, but the reason that we show, like, the reason that we say that this 11 is the proton number and not the electron number is because the electrons are the ones that they move around, or they get shared amongst atoms, which is how chemical reactions occur, whereas the protons just stay in the nucleus, and thus it's just like it's a better metric of ordering the elements. So that's just like a fun fact. You don't really need to know that. Yeah, I'm still kind of nervous doing this kind of stuff, but hopefully I can build up some confidence. Okay, looking at the syllabus, we are done with most of 2.2. Right, now you need to know the electronic configuration and some more things. So let's start with that. Right. So as you can see here, this is just like an example of an atom. Now, the main thing that you need to know about electronic configuration, in fact, before we even talk about the electronic configuration or distribution, you need to know that electrons are arranged in shells, which are, let me just show you real quick. Electronic shells are these things right here. This is a shell, this is a shell, this is a shell, and this of course is this guy right here is of course the nucleus. Electrons are arranged in pairs in each of these shells, and the first shell that's closest to the nucleus, so this shell right here, has the lowest energy level, while the shell that is furthest from the nucleus has the highest energy level. It's called the valence shell, and the electrons in the valence shell are called valence electrons. I kind of mentioned this a few seconds ago, but electronic configuration is just the arrangement of electrons in the shells of an atom. And you can do it pretty easily. The first shell that is closest to the nucleus will always have a maximum of 2 electrons. It can have 1 electron, but it can't have more than 2. 2 is the maximum. The second shell, on the other hand, has a maximum of 8 electrons. It can have 2, 3, 7, it can have 8 electrons, but it cannot have 9 electrons. And again, these electrons will be arranged in pairs. So if there were only 7 electrons here, this electron won't be present, and this guy will just be alone. Similarly, the third shell, the valence shell, will also only have a maximum of 8 electrons, again arranged in pairs. So that's just the basics that you need to know. Again, a quick tip, you can easily figure out if you're given the structure of an atom, you can figure out which element that is based by just counting the number of electrons. There might be questions that try and confuse you, and they might say that this is an ion, in which case you need to account for the gain or loss of electrons, but generally that's something you can easily do. Now, another thing that you need to be familiar with is number 1. You need to know what the period and group numbers that the period number tells you. So this right here, the period number. So the period number in the periodic table tells you the number of shells in the atom. So in the case for this atom right here, since it has 3 shells, we can deduce that this whatever element this is found in period number 3. and you can obviously deduce the number of shells if you're given the period number. The group number, just a second. Yes, the group number tells us the number of valence electrons that are present in the atom. So in the case for this atom right here, it has 8 valence electrons, meaning that it's in group 8. And again, you can deduce the number of valence electrons if you're given the group number. Right, on the topic of groups, we should talk about group 8, which is a special group. It's also known as the noble gases. Uh, the noble gases, or the rare gases, or the inert gases. As the name implies, they are inert or they are unreactive. And the reason that they are unreactive is because they have a completely filled valence shell, because they have 8 valence electrons, similar to our example right here. An exception to this would be helium. So a helium atom looks something like this. This is the nucleus, this is the first shell, and there are only 2 electrons. However, you'll notice that even though there are only 2 electrons, it has a complete valence shell, which is why it's still a noble gas. Another thing I'll say is that the 288 rule, which is how I describe electronic configuration, is only applicable to the first 20 elements, which is why I said that the first 20 elements are really important for you to learn by heart. And after that, it does become more complex. So for example, rubidium actually has 18 electrons in its third shell, but that's not something you need to worry about. Yeah, right. So now we come to the topic of isotopes and AR, or relative atomic mass. Let's start with with isotopes. Let me write that down. Now, isotopes are just atoms of the same element that have the same number of protons but different number of neutrons. What do I mean by that? Let's look at a standard carbon atom. A standard carbon atom, it has a mass of 12 and it has 6 protons, meaning that from this we can deduce that there are 6 protons, 6 neutrons, and 6 electrons. A common isotope of carbon is this. It looks something like C13-6. Again, you'll notice that there are 6 protons and 6 electrons. That hasn't changed. But because the mass is 13, we can deduce that the number of neutrons is 13 minus 6, which is 7. So in this case, you can see that these are both carbon atoms. And while the standard carbon atom has 6 neutrons, this second carbon atom actually has a different number of neutrons, which is and we call this an isotope. Now, I think it's important to take note of one thing. Even though these two isotopes have different atomic masses and different number of neutrons, they still have the same chemical properties. This is because the number of protons and electrons do not change, and thus the number of valence electrons are the same, which, if you remember, is what those are the electrons that take part in chemical reactions and thus determine the properties of a substance. And that's an important thing that you need to really put into your head, especially if you're doing the extended syllabus, which I'm assuming most of you are. Now, there are also certain isotopes known as radioisotopes which can break down in a nuclear reaction, giving out a lot of energy, and this energy includes radiation. Now, this can be useful and harmful depending on how it's applied, and common example of a radioisotope would be francium or uranium, which are the most popular ones. Okay, another thing that I forgot to mention before is that the number at the top is called the nucleon number, which is just the number of subatomic particles that make up the nucleus, basically the protons and the neutrons. And as I mentioned before, this is the proton number. So that's something that you need to remember. Now, carbon is actually a very important element, especially when you start talking about stoichiometry. So, Avogadro discovered that the carbon atom, or the standard most common isotope of carbon, has a mass of 12 in AMU. And this mass of the nucleon was used to work out the masses of all other atoms, which is why carbon is so important. You'll learn more about this in stoichiometry, and we say that the masses of all other atoms are relative to a carbon 12 atom. Thus, we call that the AR, relative atomic mass. Now, to really simplify what I'm saying here is that the AR of hydrogen is 1. What that means is that relative to a carbon 12 atom, hydrogen has a mass of 1. Yeah, I made a mistake. Hydrogen has an AR of 2, I'm pretty sure. Let me double check. Should definitely double check these things. So I'm learning with you guys, right? I think that adds a bit of personality. Question mark? No, I was right. Okay. Yeah. Hydrogen has an atomic mass of 1. Right. Now, to give you the actual definition of AR, it's basically it's the average mass of an element's isotopes compared to 1/12 of the mass of carbon 12 atom, which is just a fancier way of just saying what I explained before. And you can calculate AR using the formula AR is equals to the atomic mass of the first isotope times its percentage abundance. Let me just write that down. Atomic mass of the first isotope times its percentage abundance put that in brackets, plus the atomic mass of the atomic mass of the second isotope times its percentage abundance, and so on and so on. So the main thing that you need to take away from this is that chlorine, for example, let's do that. Chlorine is, this is a normal chlorine atom, quote unquote normal, and I have this isotope right here. It has 2 extra neutrons. Now this is found to be the chlorine atoms with a mass of 35 make up 75% of all chlorine in the world, while this guy right here makes up only 25%. Now, based on this, once you plug it into the equation below, you can find out that the AR of chlorine is 35.5. The actual, well, yeah, I mean, that's more or less it. So now we come on to bonding, chemical bonding. And there are three types of chemical bonds. We'll be starting with the first type, which is metallic bonding. So let's write that down. Metallic bonding. Right. So metallic bonding can be described as positively charged cations that are deposited in a sea of negatively charged electrons. So let me just try and draw that to display what I mean. Right. So I've decided to take aluminium as an example here, and you can see that in this case I have a bunch of aluminium cations which have a +3 charge deposited in a sea of negatively charged electrons. So these guys are the electrons and they have a negative charge. Now some of you may be wondering, where did these cations come from? Well, that will also help explain how the sea of electrons formed. Basically, if I have two aluminium atoms, they have their three valence electrons. I'm pretty sure. I think I should know this. Now, this electron, let me get a different color. This electron has a negative charge, and it's attracted to the positively charged nucleus of this atom, causing it to delocalize. Or it becomes a free electron or delocalized electron. And the same thing occurs for all the other electrons. And when you scale this up to a larger scale, you realize that all of these electrons are free or delocalized, which means that they're free to move about the metal cations. Speaking of the metal cations, you'll notice that they are arranged in a regular structure. And we say that the cations are arranged in a regular lattice structure. So the free electrons, the delocalized electrons, are free to move about a lattice structure of metal cations. That's just an easy way of describing metallic bonding in terms of structure. Another important thing I should mention is that metallic bonding metallic bonding is electrostatic in nature. I'll explain what this means in a second. So static in nature. What this means is that the negatively charged electrons are attracted to the positive cations and basically hold, and because of this, all the particles are held together very tightly due to electrostatic forces of attraction. Thus, we say that metallic bonding is electrostatic in nature. And this makes it really strong, which can be used to explain some of the general properties of metals, and we'll look at later on. Right, so as you can see here, I've made a list of the general properties of metals, and all of these properties can be explained based on what you know from metallic bonding. So let's start with number 1, high melting and boiling points. The reason that metals have high melting and boiling points is because of the electrostatic nature of metallic bonding. The bonds are very strong, meaning that you need a lot of energy to overcome these bonds for melting and boiling to occur, and thus they have high melting and boiling points. Metals are hard. Most metals are hard because of the electrostatic nature of metallic bonding. I think that's simple. And also metals are good conductors of heat and electricity due to the presence of free or delocalized electrons to carry energy throughout the metal lattice. That requires some explanation, and that's a pretty niche one. Malleability. This is going to be a little weird to explain, so stay with me here. If I have a metal lattice such as this, you can see that it's in a regular, almost crystalline structure, and I apply a force on this end. Because the cations are arranged in layers, and these layers are lubricated by the delocalized electrons, they are able to slide past one another and thus change shape due to the applied force, which is why metals are malleable. Ductility is very similar to that, except that instead of uh, really applying a force, instead of being hit when the metal is pulled, in a sense, it's pulled. And again, because they're arranged in layers and delocalized by lubricated by the delocalized electrons, they are able to slide past one another and form wires, which is why metals are ductile. Right. So the second type of bonding that we'll be looking at is covalent bonding. Now, covalent bonding is a type of bond that is formed through the sharing of valence electrons. That's an important distinction. If you write just electrons, you're likely to be penalized by the examiner. It's always good to mention valence electrons. The sharing of valence electrons, to be precise. Let me add that as well. Sharing of valence electrons. Now, what I mean by this is that, generally speaking, covalent bonds apply for simple molecules with simple molecular structures, and more often than not, it's between a metal and a it's between non-metals. So, non-metals usually have exist as compounds or exist as molecules via covalent bonding. Now, what this means, you can really think of this using examples. So, let's take hydrogen for instance. Hydrogen has one valence electron, meaning that it is highly reactive and doesn't exist as a single atom. So if I have two hydrogen atoms right here, this is the nucleus of both of them, 1, 1. Let's represent the second one with an X. Because they both need a full outer shell, the best thing that they can do is share their electrons. So the one on the left is going to give its valence electron, one of its valence electrons, and the one on the right is going to give one of its valence electrons. And now you can see, through sharing, both of them have two valence electrons. Now over here, I would like to give a rule that my teacher once told me. What you give into the world is what you gain or what you get. So A, for example, needs one extra valence electron to be complete, quote unquote. So because it needs one valence electron, it's going to give or share one of its valence electrons. The same applies to B. Hydrogen is kind of simple, but what I'm trying to say right now will be more useful when we go to more complex molecules. Now I mentioned this before, but a molecule is basically two or more atoms that are held together by covalent bonds, and hydrogen is a molecular element, which means that it exists as a molecule. It always exists as H2. Hydrogen gas is H2. So this is an important thing that you need to remember during chemical reactions involving hydrogen. We say that hydrogen is diatomic. A few other examples of diatomic molecules would be O2, oxygen, N2, nitrogen, and all the halogens. So that's group 7. Halogens are group 7, fluorine, chlorine, etc. Another thing that all of these guys have in common is that they all have covalent structures, or they all have covalent bonds. And we'll actually be looking at a few of these in just a minute. Right. So as mentioned, let's take a look at chlorine. Now chlorine has 7 valence electrons, as you can see here. Just a second. Right, I made a bit of a mistake before, but it's fine. As you can see, there are 7 valence electrons in chlorine atoms, which means that each one of these chlorine atoms needs to gain or needs to share. Basically, they just need one extra electron, and what you need is what you give, meaning that both of them share one of their valence electrons with one another to form a chlorine molecule. Now, that like 3 or 4 things that you really need to keep in mind here. Number one, notice how I use circles or dots for this chlorine atom and crosses for this chlorine atom, even though they are both chlorine atoms. This is an important thing that you need to do to show that to like basically just distinguish between the electrons. Number two, I want you to notice that in the previous example, which involved hydrogen, let's take a look at that. Since there were only one valence electrons in both of them, I didn't really draw anything here because there's nothing to draw. However, I didn't draw anything here because there's nothing to draw. All the valence electrons are being shared. But that's not the case with chlorine, because in chlorine, only these guys are being, in chlorine, only these guys are being shared. These valence electrons still need to be shown in your final diagram. That's number two. Number three, 2 shared electrons or one pair of shared electrons forms one covalent bond. So what this means is that since 2 electrons in total are being shared here, or because there's one pair of shared electrons between both the chlorine atoms, we say that the chlorine atoms are bound together by one or a single covalent bond. And we can represent this by, so this represents a chlorine atom being bound with another chlorine atom via a single covalent bond, and this covalent bond shows that two shared electrons. That's a really roundabout way of saying it, but it's the best explanation I can muster up. Right. The second molecular element that we look at is oxygen, O2. It's kind of similar to chlorine, aside from the fact that because there are 6 valence electrons, an oxygen atom needs 2 extra electrons to be complete. Meaning, again, what you need is what you give. So because an oxygen atom needs 2 extra electrons, it will give or share 2 of its electrons, which is why you can see that I've made 2 of these 2 electrons red and these 2 electrons red. And thus, in this covalent structure, you can see that there are 2 pairs of shared electrons in an oxygen molecule, or there are 4 shared electrons, whatever suits your fancy. And this also means that there are 4 pairs of lone electrons. So the electrons that are not being shared are called lone electrons. So 4 pairs of lone electrons or 8 lone electrons, depending on how you want to look at it. And again, remember how I said one covalent bond is 2 shared electrons? So 4 shared electrons leads to 2 covalent bonds. So we can represent an oxygen molecule as having a double bond between its atoms, represented by these 2 lines. And that's about it for oxygen. Right. So the third molecular element that we are going to be looking at is nitrogen. Now, nitrogen has 5 valence electrons, meaning that it needs to get 3 valence electrons to be complete. What you need is what you get. So it's going to share 3 of its valence electrons with the other nitrogen atom. As you can see here, these 3 are the ones that are being shared by one of them, and this means that there are in total 6 shared electrons or 3 pairs of shared electrons with 4 lone electrons or 2 pairs of lone electrons left. And this is an N2 molecule along with its covalent structure. Again, 2 shared electrons form one covalent bond, so 6 shared electrons will form 3 covalent bonds. Hence, you can represent a nitrogen molecule as having a triple covalent bond. And yeah, that's about it for nitrogen. Right, so now we come to the topic of covalent compounds. Now, covalent compound, this is really the same thing that I've been doing so far. It's just that right now we are looking at compounds which have more than one kind of atom. So as you can see, rather than having 2 hydrogen atoms, we have a hydrogen and chlorine atom. And since I have already started, let's just begin. So this is HCl, hydrochloric acid. It's the same concept. The only thing I want to point out is that notice how there are no lone electrons on the hydrogen atom, but there are 3 pairs of lone electrons on the chlorine atom. And you can represent hydrochloric acid as like this. The next thing we have here is water, H2O. Something we all know. Again, a very similar concept. The only thing I want to point out is that I want you to look at the lone electrons that are present on the oxygen atom. And pro tip, usually is the key word. Whenever hydrogen is present in a simple compound, it's likely to have 4 lone electrons, but that can obviously vary on a case-by-case basis. And you can represent water as like this, based on its structure. Now we come to ammonia, NH3. Ammonia, NH3. Again, notice the lone electron that is present on the nitrogen atom. And yeah, again, the concept is very similar. There are no lone electrons on the hydrogen atom because they only have 1 valence electron which is being shared. You can represent ammonia like this, yeah. Again, nitrogen has 3 separate bonds with hydrogen atoms, with 3 separate hydrogen atoms. It's not something like this. This is wrong. This is correct. This next one is methane, CH4. Yeah, methane, CH4. Now, methane again, very similar concept. Over here, there are no lone electrons whatsoever. That's because carbon has 4 valence electrons, and all 4 of these valence electrons are being used to form covalent bonds. So you can represent it as this, H. So this is correct. Don't do something like this. This is wrong. Never do something like that. And over here we have carbon dioxide, CO2, carbon dioxide, CO2. Now, one major thing you need to take into account is that in a way it's kind of similar to water because there are 3 different types of atoms, but you'll notice that the carbon dioxide molecule, has a linear structure, which is what we use to describe its structure. It's a linear molecule, rather than this upside down Mickey Mouse face that you can see for the water molecule. The reason that carbon dioxide is a linear molecule is because this set of shared electrons Wait, yeah, it's because uh, these shared electrons and these shared electrons, they both have a negative charge, and hence they repel each other, causing it to have such a linear shape. Right. So these are two more covalent compounds, and these ones are slightly harder, but the concept is the same. So this first one is called methanol. It's a type of alcohol. Uh, Methanol is CH3OH. Uh, and again, the concepts are very similar. The only thing I'll say is that because there are three types of atoms, I've used a cross, I've used a circle, and I've used a filled in dot to represent the valence electrons. And the structure is something like this. Yeah, that looks about right. That's the structure of methanol. The second one is called ethene. It's a type of alkene. It's C2H4, right? And again, it's very similar to what we've been doing so far. The only thing I'll say is that there is a double bond between the carbon atoms. So you can see it's like this: H, 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 and H. And that's about it for covalent compounds. Now we come to the third type of bonding, which is called ionic bonding. Now, ionic bonding is a type of chemical bonding that involves the transfer of valence electrons. Let's write that down. Transfer of valence electrons. Again, that's an important distinction from just electrons. Covalent bonding involves sharing valence electrons. Over here, the electrons are transferred from one atom to another. You'll understand what that means in a few seconds. I'm assuming we all know about how ions are formed. Ions are just charged atoms that are formed when an atom loses or gains electrons. And it's best to display this using an example. So let's look at sodium chloride. It's table salt, NaCl. Sodium chloride. Now, what happens is that sodium, Na, has one valence electron, while in this case you can see that chlorine has 7 valence electrons, right? Now, when these two react, since sodium has less than 4 valence electrons, it gives up its electrons to the chlorine atom, and this causes the formation of a sodium ion, Na plus. As you can see, it doesn't really, its valence shell is technically empty, but its second shell will now have 8 electrons, Na plus, which is a cation, and you'll also have chlorine, or a chloride ion, sorry. A chloride ion looks something like this. And yeah, notice how I use this circle to show that this electron came from the sodium. So this basically ionic bonding involves the formation of ions between the reaction of a metal and a non-metal. So sodium is a metal, chlorine is a non-metal, and when they react, one of them gains electrons while the other loses electrons, and the electrons that are gained and lost are basically transferred from one atom to another, and this leads to two oppositely charged ions forming, which attract one another, and this electrostatic attraction is what we call ionic bonding. And ionic compounds are just the actual products that are formed. So when the metal atoms lose their electrons to the non-metal atoms and all the bonding stuff happens, that you get an ionic compound. Yeah, that's about it. And another thing I should mention is that ionic compounds actually have a lattice structure and they have no overall charge, which is an important distinction to make. Now, a very, very, very important thing that you need to know for the IGCSE, if you're studying the IGCSE syllabus, is that it is the differences between ionic compounds and covalent compounds. So I think we should start with that. Ionic compounds and covalent compounds. Covalent compounds. Now, ionic compounds have high melting and boiling points, high melting and boiling points, and contrary to this, covalent compounds have relatively lower melting and boiling points. And this is because ionic bonds, because they're electrostatic in nature, you need a lot of energy to overcome them in order for melting and boiling to occur, and so that the ions can break apart from their lattice structure. And yeah, that's just the reasoning for why they have high melting and boiling points. The second property of ionic compounds that they are soluble in polar solvents. And polar solvents isn't something you need to know in the IGCSE scheme. The main thing you need to know is that they're soluble in water. So water is a polar solvent. So just know that they're soluble in water. And covalent compounds aren't soluble in water. Rather, they're soluble in non-polar solvents. You don't need to know this for the IGCSE scheme, but they are soluble in non-polar solvents. For example, benzene, toluene. I don't think this is the right spelling, but toluene is a non-polar solvent. Yeah. The third property of ionic compounds are that they conduct electricity. They conduct electricity only. Calm down. All of you keyboard scientists out there, just calm down. They conduct electricity only in their melted or aqueous state. This is a very important thing. They're solids at room temperature, but they don't conduct electricity at room temperature. But when you melt them or when you make a solution using them, the ions in the ionic compounds become free to move, and so they are able to conduct electricity, or they are able to conduct charges. And I mentioned the fifth property here, or the fourth property. They're solids at room temperature. Solids at room temp. Solids at room temp. So covalent compounds don't conduct electricity, and they are usually liquids or gases at room temp. So hydrogen is a gas, water is a liquid, etc. at room temperature. Yeah, and that's the differences between ionic compounds and covalent compounds. It's very important in the IGCSE scheme. Right. Now we move on to macromolecular structures, macromolecules. Now macromolecules are substances with giant covalent structures. They have giant covalent giant covalent structures. Right. Now, when we say they have giant covalent structures, it's still, these are still covalent compounds. It's just that their structures are really, really big. And the best example for macromolecules would be diamonds, and graphite. Both diamond and graphite are carbon. They're just allotropes of carbon, which means that an allotrope is just one or more alternative forms of an element. So carbon exists as many different allotropes, and two of these are diamonds and graphite. And I think since we are all familiar with these two, and we all know that diamonds and graphites are two very different things, which is ironic since they're both just carbon. The main difference arises in their structure. First of all, diamonds have one carbon atom that is covalently bonded to 4 other carbon atoms as such. Now what this means is that all of the valence electrons in a carbon atom are being used to form bonds. And thus this makes carbon very strong and hard, but this also means that it doesn't have any free electrons, so it doesn't conduct any electricity. What I've drawn here is just like a small version of its structure. In reality, it stretches out a lot. And I already mentioned one of diamond's properties. It's hard. For the same reason why as it's hard, it also has a high melting point because all of its valence electrons are being used to form bonds. And again, it doesn't conduct electricity, which is the third property of diamonds. Now we look at graphite. Graphite is also carbon, but here it only uses 3 of its valence electrons to form bonds. So you get so each of these retain one of the electrons. Again, these like stretch out. It's just a small section. This is just a small section. But yeah. This means that graphite, because it only uses 3 of its valence electrons, is not as hard as diamond. However, because it still retains delocalized electrons, it, number 1, can conduct electricity, and number 2, it's slippery, or the layers can slide over one another, which makes it viable as a solid lubricant, which is one of its uses. That's another thing that you need to know, which is the uses of both of these. So diamonds are used in jewelry, but rather than saying jewelry, IGCSE likes when students say that diamonds are used in drilling and cutting tools, which is the more practical use for diamonds. Graphite, as I mentioned, is a solid lubricant, and it's also used in, it's a solid lubricant. That's probably the best example. Right. So the third macromolecule that the IGCSE syllabus requires us to look at is silicon dioxide, also known as silica, SiO2. Now, unlike graphite and diamond, silicon 4 oxide is an actual compound, whereas the previous two were just allotropes of carbon. Over here, when describing the structure of silicon oxide, you basically just need to mention that one silicon atom forms covalent bonds with four oxygen atoms, and each oxygen atom forms two uh, uh, forms bonds with two silicon atoms, as you can see from my very rough sketch. And also, silica is the main mineral that you can find in quartz, and quartz itself is found in sand. And it has many properties that are similar to diamonds in the sense that it is hard, it has a high melting point, and it doesn't conduct electricity. And the few uses of silica include uh, using it as sandpaper, like using it to make sandpaper, using it in bricks for lining for furnaces, and also using it to make mortar for like roads. And yeah, that's about it. And yeah, and with that, we've officially finished Unit 2 of the chemistry syllabus. I hope you enjoyed, and I hope you at least took something away. At the very least, you know what to revise for your exams. And yeah, please consider subscribing. Goodbye.